Hello everyone, welcome to Algo-holic, the place where you learn not just the solutions but the thought process behind solving problems.
Today we're solving the problem majority element. We're given an array nums of size n. We're supposed to return the majority element. The majority element is anything that appears more than n by 2 times, and we may assume that the majority element always exists. So if we have an array of size 100, we need to find that element which appears at least 51 times. Let's look at an example 323. The answer is 3. Here 2 appears 4 times and 1 appears thrice, so the answer is 2. The simplest solution is to just loop through the array, find out how many times each and every element appears, and store that in a hash map. So if we have 3, 2, 4, 3, and 3, this is the hash map. The pointer starts over here, so we encounter a 3, so this is going to be 1. We encounter a 2, this is going to be 1. We encounter a 4, this is going to be 1. The second 3, so this is going to be 2. And 3 again, so this is going to be 3. In the end, we just have to return the max of this, so it's going to be 3. Now, this is a decent solution where the time complexity is going to be big of n because we just loop through the array once, and the space complexity is also going to be big of n because if there are n by 2 unique elements, the size of the hash map is also going to be that. Now, can we do better? Because the question asks us to solve the problem without taking extra space. Now, it is possible to solve this problem without taking extra space, but we might have to compromise on time. For example, in the previous method, we stored how many times each and every element occurred in a hash map, and then we got the max of it. Instead of that, we can check the number of times the current element occurs in the array and check if that is more than n by 2. We repeat the process for every unique element in the array until we find the element. For example, if we have 3, 2, 5, 5, 5, and 5, the majority element over here should appear more than thrice. So it's going to be 4 since it cannot be decimal. We start off with 3. How many times does 3 occur? We make a pass and we find that out. 3 occurs only once. 1 is not equal to or more than 4, so we discard it. Next, we check 2. How many times does 2 occur? 2 also occurs just once. So we again discard it since 2 is not equal to or more than 4. We check for 5. Now 5 occurs 4 times. Now, since we found that 4 is more than or equal to 4, 5 is the majority element. Now, what is the time and space complexity of this? Space complexity is going to be big of 1 because we're not taking up any extra space, but the time complexity is going to be n squared, which is very bad. Now, how can we manage both space and time in such a way that space is going to be big of 1 and time is going to be just big of n? Now, this algorithm is not very easy to come up with, and it's one of those algorithms that is taught in school early on so that this becomes like a base knowledge for you to build upon. But I'll show you how to visualize it and it'll help you understand why this works. In the first method, what we did was we counted the number of times each and every element occurs, stored it in a hash map, and got the max of it. Instead of that, what if we just assumed that the current element is the majority element, stored the count of only that? Let's see how that would play out. We have majority, a variable, and count, another variable. Majority is initially null, and count is initially 0. Let's say the array looks something like this, and the pointer has still not started. The actual majority that we know of is m. So I'll show you how we get that. We start off the pointer. Initially, it's at n. So we assume that the majority is n. Count becomes 1 because we just encountered it. We move the pointer. Now it's at m. M is not the same as n over here. So what if we just increment the count variable? If we increment the count variable, we are just going to end up with the size of the array. And it's not going to give us any meaningful information. So we can't do that. What if we skip it? If we skip it, we are just going to get the number of times n occurs, which again doesn't give us any meaningful information. So what do we do now? What if we decrement the count variable? So 1 becomes 0. Now what happens now? It feels like we just lost meaningful information by just doing that. But in reality, what we did was we shortened the length of the array without changing the actual result. Now think about it. Let's say there is an election where there are two parties, and two people who would vote for different parties. Now, them showing up on election day and voting is the same as them not voting because their votes technically cancel each other out. That's exactly what's happening over here. And I'll show you why this works in a problem where there aren't just two parties. There are multiple numbers here, right? But it would still work. This works because there are two scenarios in which the cancelling out happens. The first one is where the majority element is next to a non-majority element where both of them get cancelled out, or two different non-majority elements both get cancelled out. Either ways, the result is not going to be affected by it. I'll show you an example without arrays. So let's say the majority element occurs 8 times. A non-majority element n1 occurs 2 times. A non-majority element n2 occurs once. And let's say this is it. So let's say we have a situation where we have m and n1 next to each other, and they both are going to be cancelled out. So what is going to be the result in this box when the cancelling out happens? When one m is cancelled out with one n1, this is going to be 7, this is going to be 1, and this is going to be 1. So in the new array, as you can see, the majority element is still m. The result is not affected. What if we cancel out n1 and n2? What happens then? This is going to become 0, this is going to become 0, but the majority element is still going to be 7. The result is not affected at all. So this is why this algorithm works, and it doesn't matter what order the array is in, it is always going to work. And I'll show you that as well. Let's say the majority element is in the front of the array. We have majority variable with count. Majority variable is currently null and count is 0. The idea here is that we nullify majority variable whenever the count is 0. Initially the count is 0, so the majority element is also nullified. We reach the first element. So count becomes 1, majority becomes 1. Sorry, majority becomes. We reach the second element, count becomes 2, majority is still 2. Third one, count becomes 3, majority is still m. Here, count becomes 2, and this is still m because we only nullify it when count gets to 0. We found another n, so this becomes 1. This is still m. In the end, all we have to do is return this variable. So this works when the majority element is in the start of the array. Let's see a situation where the majority element is at the end. Initially, majority element says null and count as 0. We start off the pointer, majority element becomes n, and count is 1. We move the pointer, this is still n, and count becomes 2. Move the pointer, this is still n, but count becomes 1 since m is different from n. We move, count becomes 0, and whenever count becomes 0, we nullify the element majority here. So there's nothing over here, so just null. Now we move it over here, and count becomes 1, and majority becomes m. In the end, we still got the answer. Let's see a situation where everything is scattered. M, N, M, N, M. Majority variable and count. Count as 0, majority variable is pointing towards null. We get count as 1 and variable as m. Now we found a different element, so count becomes 0 and this becomes nullified. We found the first element again, count becomes 1, this becomes m. It gets nullified again, so it gets nullified since count was 0. Now we found an m, this becomes m and count becomes 1. Now in the end, no matter what happens, we're always going to get the right answer. This algorithm is not going to tell you how many times the element occurs, but just point at that element which is the majority element. I can't think of a real life situation where this algorithm is employed, but I feel that this is a great algorithm to understand, which helps you come up with solutions for much bigger problems. The time complexity of this is of course big of n because we are just looping through the array once, and the space complexity is going to be big of 1 because we're just using two variables for storing any data. Let's quickly code up the simplest solution where we have a hash map We loop through the array. We check if the item is present in the hash map. If it is, we increment it. Else we add it into the hash map. And then we have another loop, this time through the hash map. We check if the value is more than half of length of the array. So if it is, we return the key. Yep, this works. Let's now look at the brute force solution where we have, now we need to find the count of each and every element in the array. So we can just use count. This is not going to change the time complexity. It's still going to be n square. If count is more than length of, return the item. Yep, this works too. Now let's look at the final solution, which is the Biomore voting algorithm. Now let's say the majority element is initially null. So this is none and count is 0. We loop through it. If count is 0, what do? We update the majority variable to the current element and we increment count. Next, elif, we check if the current element equals the majority element. So if item equals majority, and if it does, we increment the count variable again. Now, if neither of this is true, we decrement the count variable. This just means that count is not 0, but the current item is not the majority item. So in this case, we make it -1. In the end, all we have to do is return majority. Sorry, this has to be, this works. And for some people, you can change this to candidate so that in terms of voting algorithm, this might be easier for you to visualize, but doesn't really matter. So let's go ahead and submit it. Yep, it works and it is the best solution. C++ code looks pretty much the same, where we have candidate and count initialized to 0. If count equals 0, we update the candidate and increase count. If item equals candidate, we just have to increment count, else we decrement count. In the end, the candidate variable will have the final answer. Java code looks pretty much identical, where if count equals 0, we update the values. If item equals candidate, which is the assumed majority, we increment count, else we decrement count. In the end, we're just returning candidate. So that's all for today. I hope you found this video helpful. Your feedback helps me make better content, so please share your thoughts in the comments below. I'll see you in the next one.